I can stir my tea so as to cause a circular motion. Inertia keeps this primary flow going. The tea leaves are a little denser than the liquid and settle slowly toward the bottom. Since they are denser, we might expect centrifugal force to throw them outward and to find them around the perimeter of the bottom of the cup. But look, they collect at the center. The cup has no drain, but still we find evidence of a flow toward the center near the bottom. We've made an experimental model of this flow in order to examine it more closely. This square box has a circular container inside. It has been rotating around its axis for a couple of hours, bringing the liquid inside to a state of uniform rotation. I can stop the rotation, but the liquid, due to its inertia, will continue to rotate at uniform velocity, except near the wall and the bottom, where a boundary layer will build up. As a first approximation, we will assume that all particles travel in circles around the center of the cylinder, making allowance for the fact that the boundary layer moves at a slower rate than the rest of the flow. We will call this first approximation the primary flow. In order to observe this flow better, we have stretched a very fine wire vertically to the bottom of the tank. Hydrogen bubbles electrolyzed from this wire are stripped off by the flow. By pulsing the current, we can create a series of bubble lines. These lines show up very much better if we dim the room lights. From above, it appears that much of the flow does indeed follow a circular path. Near the bottom, however, a portion of the flow appears to go inward. We can now look into the tank at a tangent to the flow past the wire. And incidentally, we can see that the reason for the square box is to eliminate optical distortion. In this tangential view, we see that the simple circular flow occupies the greater part of the depth. The inward flow extends only a short distance from the bottom. This inward flow is a departure from the assumed primary flow and is what we call the secondary flow. And now let's look inward in a radial direction, that is across the streamlines. We see the circular flow as before and the effect of the boundary layer near the bottom. But notice that this boundary layer appears to affect about the same portion of the total flow as did the inward curving secondary flow. If we look at the radial and tangential views side by side and in the same scale, it becomes clear that this secondary flow occurs within the boundary layer. The inward movement in the boundary layer seems to be directly associated with the reduced tangential velocity in the boundary layer. Our simplified model has given us some insight into this particular secondary flow. Is it the reduced tangential velocity in the boundary layer which results in the spirally inward flow? Let us consider a fluid particle moving on a circular streamline. The pressure force on the outside must be larger than the pressure force on the inside in order to result in a net pressure force inward. The pressure gradient, you will recall, is described by Euler's equation, normal to the streamline. Suppose that a particle in this pressure gradient has higher than normal velocity. It will then have to follow a larger radius and be carried outward. If it has a smaller velocity, it will have to follow a smaller radius and be carried inward. In our experiment, the pressure gradient is established by the main circular flow and impressed on the boundary layer below. The slower moving particles in the boundary layer find themselves in just this situation. Same pressure gradient, but lower velocity, and therefore are swept inward. Tea leaves in the bottom of the teacup are carried to the center. Dye in the bottom of the sink vortex sweeps inward. A predictable secondary flow explains each phenomenon. Suppose we invert the sink vortex by taking the water from the top instead of the bottom. I have closed the drain at the bottom and arranged this siphon to withdraw water from just below the surface. And now I will put some dye near the bottom in the boundary layer as before. You ever see a tornado?